Good morning, students. So we will continue our discussion of linear pipelining. So what we studied is that parallel processing is infeasible because in order to execute all instructions simultaneously, we need that many number of processes as the number of instructions, which is impossible, which cannot be done, okay, which is practically in computing terms is infeasible. And if you do execution of instructions serially one after the another, it will take a lot of time, okay, the efficiency will be too low. That's why we go for linear pipelining, in which what we do is we maintain a parallelism, but at the same time we see that every component or every stage of instruction execution is busy, okay. So in terms of the stages, first we have instruction fetch, instruction decode, operand fetch, execute, then after that write back, okay. These are the stages. And what we do in pipelining is, I'm just going through a quick revision of yours, okay. Then in instruction 2, what we do at the same time, decode and instruction fetch circuits or stages are busy, and this is instruction decode, then operand fetch, execution, WB. So on an average, to carry out an instruction, how much time is needed in case of pipelining is k plus n minus 1 clock cycle, or we can say k plus n minus 1 into TP, time period, okay. So that much time is required in terms of seconds, okay. This is what the time is, time consumed by the pipeline structure. In case of serial structure, it may take n into what is the number of instruction and time period for, sorry, not time period, time to execute one instruction, that is k. K is the time to execute one entire operation, okay, because there are k stages in it. So suppose k can be written in terms of second or whatever, but this is more or less the time, okay. K n into k seconds. So now this was all about yesterday's class. Today we will learn the concept of speed up, okay. So what do you mean by speed up? Speed up means, with comparison to serial processing, how much better the pipelining system did is defined in terms of speed up, okay. So speed ups tell us that pipeline structure is better by what factor, okay, how many times it is performing better than a serial execution is defined by speed up, okay. So we will solve a few problems and it will be clearer for you. Okay, speed up. So speed up is defined as factor by which pipeline processor is better or efficient with respect to non-pipeline processor, which is defined as, by mathematical formula, time taken by non-pipeline processor by time taken by pipeline processor. So this is the formula for speed up, okay. So what does speed up says? To be crystal clear, you should get this fact straight, that speed up means it is the measure by what amount the pipeline structure is performing better or is efficient than the non-pipeline structure. Clear? This is what speed up is. So in terms of mathematics, it's very simple, right? So suppose the time taken is, suppose the time taken by non-pipeline structure is 1000, let's say 1000 seconds, and time taken by pipeline structure is 100 seconds. So by how many times it's performing better? 10 times, right? Because 100 into 10 is 1000. So by 10 times pipeline structure is performing better. Okay? Because the speed is 10 times less in case of pipeline structure rather than non-pipeline structure. Okay? You got the idea. So let's take an example and solve this question of speed up. We'll take a few examples and calculate speed up in a given scenario. Okay? So suppose, let's say the question is, the time period is given, or we can say frequency is given, because if frequency is given, you can easily deduce time period. Frequency equal to 1 by t. Okay? So suppose frequency is 1 megahertz. Okay? You are given n is equal to 100 instruction. Okay? And k, that is number of stages, is suppose 5. Okay? And each stage take 2 nanosecond per stage delay. So what is the speed up is the question. Can you solve it? Could you try? We have to usually find time taken by pipeline processor, time taken by non-pipeline processor, and we have to divide it. Okay? So what we can do is, first we have to find the time period. What is time period is? Tp is what? 1 by 1 megahertz. Megahertz means 10 to the power 6. Okay? So 1 by f. T C implies T is 1 by f. So we are given frequency, we have to find time period. So Tp is 2 to the power seconds. So 10 to the power minus 6 seconds. So this is what? 1 microsecond. So this is the time period is. Now time for one instruction we have to find. So what is the time for one instruction here? See, there are 5 number of stages. So for one instruction, how many time is taken? 5 stages into each stage takes 2 nanoseconds. We can make it 2 milliseconds because it's millisecond, it will be easier for you. Not milli, we are getting micro, right? Let's say stage delay is 2 microseconds. Okay. So what is the time for one instruction? Any one instruction, Ti takes how many time? 5 into 2 microseconds, it is 10 microseconds. Okay. So one instruction takes 10 microseconds. With non-pipeline architecture, PNP, what will it take? One instruction take 10 microseconds, then 100 instruction, because here n is 100, will take 100 into 10 microseconds, that is 1000 microseconds. One aspect we got it. Okay. Now with pipeline architecture, how much we need? We need k plus n minus 1 into Tp. That's the formula, right? Time with pipeline. So what is k? 5 plus n means 100 minus 1 into time 1 microsecond. Time period 1 clock cycle is 1 microsecond. So how much it is? 104 microseconds. So what is the speed up, guys, then? Speed up is 1000 by microsecond will be cancelled, 104. Okay. So you can solve it. It will be nearly what? 9 point something. Okay. So this will be 9 point something. So that's the speed up. It is almost 10 times faster. Okay. So this was about speed up. Now you need to understand that pipeline may not be always smooth. Okay. Sometimes there are dependency. When there are dependency, we call it that the pipeline may face some hazards. Okay. So what is a hazard in a pipeline? Suppose pipeline dependency, or we can say hazards. So what are hazards mean? Suppose in pipeline we are working on stages. Each instruction completes a number of stage. It may be 5 stage or 4 stage. But it may not so happen that every stage is working or getting data smoothly. In some cases, an instruction may take longer time. It may take few seconds more to complete its own stage, or it may be the case that the data that it needs is not ready. Okay, the data has to wait in the loop. The processor has to halt for some time until data is ready, because there are various addressing mode. Sometimes we may have to take data from memory. Sometimes it is readily available in registers. So there are cases where time may be of issue. Okay, some may take larger time, some may take smaller time. In such case, the pipeline may not run as per these ideal conditions. That is, the time may not be exactly k plus n minus 1 clock cycles. It may not be true. In such cases, we say the pipeline is going through hazards. Okay, hazards may be of various type. One is data hazards, when data is not available. The example I gave is sometimes data is present in memory, so it may take longer time to reach to that memory location. Okay, so that's why in such case we say that the pipeline is facing data hazard. That's why it has to wait a longer time. Sometimes we have to go through structural hazards. That is, structural hazard means when the hardware is not available, enough hardware is not available. Suppose there are two instructions, one is multiplication and one is addition. Suppose addition takes 3 nanoseconds and multiplication takes 5 nanoseconds. Then in such case, if the multiplication is getting executed first, and then after that addition is taking place in the next instruction, then the above instruction will consume 5 nanoseconds. So the next instruction has to wait. Although it can complete faster, no, the second instruction, that is the addition, will complete its execution faster within 3 nanoseconds. And this is 5 nanosecond multiplication. This is addition. Suppose this is I1, this is I2. So I1 is executing much. Sorry, suppose this is I1. First we were executing I2. Now suppose multiplication is already, happening, but addition cannot start. Although it is just only 3 nanosecond, because first we have to complete this 5 nanosecond. So it has to, the addition operation has to wait for multiplication to first, get completed. After the completion of I1, then only I2 can start. Okay, so such case is called when at the same time only one circuit is available and it is busy and it cannot allocate itself to the second operation until first operation is completed, is called structural hazard. Okay, when there is a mismatch or when there is a demand of an hardware by multiple instruction at the same time, then we call it a structural hazard. So what is the structural hazard, to be precise? So exactly what structural hazard is, that when there is a demand for a particular hardware or particular circuit or a particular stage by multiple instructions. Okay, when multiple instruction demand for the same stage, we call it a structural hazard. Okay, so these are more or less about the hazard. So I think we have covered almost every area of pipelining. That was all you needed to know. So you may practice some more problems on speed up factor. Okay, so I'll share some model questions with you guys. and you can the better you practice, the better you will understand on what kind of scenario a pipeline works. Okay, so you can refer to the book William Stallings. They have explained very beautifully the concept of pipeline. Okay, so this is all for today. We will continue with the topic hardware multi-programming and vertical micro-programming, and not multi-programming, excuse me, it is micro-programming. Okay, the kind of micro-programming we need to understand, there are two types, that is hardware and vertical. We will study them in the next class. Okay, so this was all about parallel processing and linear pipelining, and we will discuss next the multi-programming concept in the next class. Okay, thank you.